Okay, so I mentioned that I would talk about how you could potentially figure out that quartic polynomial by hand from that data. So I'm going to go ahead real quick and write down. So we had n dots and f of n regions. If I wanted to use this information to create a quartic polynomial to model it, first thing that we have to know is we're going to have some constants that we need to solve for. But we do know the general form. So here's our general form. And I know that when I plug in 1 for x, I should get 1 as the output. So if I plug in, I used x there, but n here. So it's not very important. I just want to be consistent with at least my equation matching. So when I plug in 1 for x, I'm going to get a times 1 to the fourth, which is just 1. Same thing, plus b plus c plus d plus f is equal to 1. Because we already know there's one region. When I plug in 2, I'm going to get 2 to the fourth power times a, which is 16, plus 2 cubed, which is 8, plus 2 squared, which is 4, equals 2. And so I've got these equations and they all have 5 variables in them. So if I want to create a system of equations to solve for this, I need to have the number of equations equal to the number of variables that I have. So since I have 5 variables, I'm going to need 5 of these equations. And so there we have 5 equations. I picked 1 through 5 because those are like the easiest looking numbers, but it doesn't matter. Any 5 points will be enough. So now the thing that we need to do is start eliminating or substituting some of these variables. So that is done just like when you have a system of equations that you would have seen maybe as early as middle school. Um, If I have something like this, I have a couple ways I can solve. I can either solve for a variable, plug it into the other, or I can multiply and try to get things to cancel out. So the same concept applies for these systems. They just have a lot more variables. So for example, I could solve for A here by subtracting B, C, D, and F to the other side, and then I could plug that in to A right here. And now I've eliminated the variable A from this equation. And I can repeat that process. I can solve for B here, plug that in, and plug in what I have for A and what I have for B, and get an equation with just C, D, and F, and so on. We can also do elimination by multiplying. For example, I might multiply this whole equation by negative 16 and then add these two equations together where that negative 16a and that positive 16a are going to cancel out. And that would give me a new equation, which would be, and I can take this equation and I can decide if I want to do substitution or elimination and try to start canceling things out in other equations. And so it's a little bit of just this guess and check, canceling things out until we end up with an equation with just one variable and we plug it in. So it's possible to do by hand. And the concept of it isn't all that crazy. But when you have this many variables, it's very tedious. And when you're doing stuff by hand, it's really easy to just accidentally make a mistake. This is where a connection to linear algebra comes in. So linear algebra is actually really useful for solving more complex systems of equations like this, what we can do is when we're doing all that multiplication and canceling out, we are really just caring about what the coefficients are and how they're interacting. So we can represent this whole system with what's called a matrix of just the coefficients and what the equation is equal to. So for example, that first one would be 1a, 1b, 1c, 1d, 1f. And I like to put a line here, and that whole thing is equal to 1. And the next one will be 16, 8, 4, 2, 1, and it's equal to 2. And so now we have a matrix. And we can do basically the exact same thing to try to reduce this into what is called echelon form, where every row on this side has one column with a 1 and the rest zeros is the goal. Because what that is basically doing is saying, okay, well then, if only this spot has a 1 and the rest are zeros, then that would tell us, for example, 1, 2, 3, 4, 2. This would tell us that A is equal to 2 if we had something like that. So I just made that up. And this makes it a little bit easier because we don't have a bunch of variables running around. So I could do that same thing that I was just showing with elimination, where I could multiply this whole thing by -16 to get, and then I have my other one, add those together with this new one. So I could say, okay, we did some multiplication and addition, and now I have an equivalent or another true equation that I can work with. And then I might say, ooh, those cancel out and get 0. I'll try to add those, and then I'll swap this one out with one of my new equations. And we just sort of repeat that process, but we've got now a little bit more organized way to do all of that. And so that's how you can use linear algebra to solve this. For sake of time, there is technology out there that does that for us. So we want to get this into reduced row echelon form. We're going to use that same matrix that we had before. And so the size of the matrix here, we have rows and columns. So we have 5 rows and we have 6 columns. And then we're just going to put in the numbers that we had. And then we're going to click calculate. Here we can tell what all of our variables are. So this column was A, B, C, D, and F. So we end up with 1 over 24 x to the 4th minus 1/4 x cubed plus 23 over 24x squared minus 3/4 x plus 1. And that matches the formula that we got from Desmos.